If there is one religion I have in my group, is that we obey the laws of thermodynamics. Energy can't be created nor destroyed, you know that, so I'm not going to spend any time on it. But it's it's a postulate. It's how we formulate thermodynamics. It's not just an observation. The second law of thermodynamics, you might have previously thought that it's complicated, but remember, now this is a definition that comes out of our equations. The entropy of an isolated system not in equilibrium will increase over time and approach a maximum when it reaches equilibrium. That was a mouthful. So equilibrium has to do with a system that is changing the distribution over particles over state. We can still have individual particles move, but if I have two states, I need to have as many particles go in one direction as the other. As long as the average distribution of states is the same, we are in equilibrium. What this says is that if I'm not in equilibrium, if there is a net motion to various states, what's going to happen is that the entropy will keep increasing over time. And if you remember, the entropy had to do with this logarithm of the number of potentially different ways we can observe the system. And that literally just means that if the particles are free to move, they will just exploring all the possible different states until they have tested all of them, and you will eventually observe them in any random combination of states. And when we have all these random combinations of states, I can't really find more states, and that's when we have a maximum in entropy. And at that point, we're going to start being at the states where we see an equal number of particles go from A to B as from B to A. This comes out naturally from the way we define things. It's not an observation. The other thing that I didn't touch upon is that entropy here, to anything we define, we're going to need to have a zero value somewhere. And this is one of the few cases, I feel, where physicists have been good enough to actually agree on the absolute scale. The obvious part, if we're talking about different states and order, let's put that at absolute 0 Kelvin. Any system I have, at absolute 0 Kelvin, there's going to be one specific ground state. Nothing moves. One state, what is the logarithm of 1? That is 0. It makes perfect sense then to say that the entropy is 0 at absolute 0. And in fact, unless I added a constant, it would actually have to come out naturally from my definition too. So these three laws of thermodynamics are arguably the only thing that will never change in physics, because they're not based on observation. They're based purely on math and our not really assumptions about systems, but our definitions of systems. And unless we change those definitions, these laws cannot change. So they're absolute and exact. And in particular, it's another example of things that might look easy, but they're significantly deeper than you might think.